Today we're going to finish DMA, then we're going to talk about buses, synchronous and asynchronous buses, then we're going to talk about memory, and then we're going to talk about what I actually think is the most interesting part of the course, and that's how the hardware interconnects with each other in order to implement these instructions. You know, we take a whole lot for granted when we use a computer. Everything has to be designed and figured out and put together in that thing to make it do what it does. And when they get this small, it becomes incredibly amazing. So, you know, we're only touching the high points. If you actually went into a computer engineering program, you would delve into the details of what we're talking about. So we're only touching the high points. You can appreciate that there's a whole lot of detail that goes on underneath the scenes. Okay, so what we're going to finish today is DMA, which is direct memory access, which I said is a way that we can efficiently transfer large amounts of data between the main memory of the computer and some external memory device like a hard drive or optical drive or, you know, solid state drive, something like that. Because we don't want the processor to have to, you know, go fetch the first word of the block of data, bring it back into the processor, and then write it to the disk, then go get the next word, bring it back into a register in the processor, write it to a disk. We don't want to do that. Highly inefficient. Instead, we want to use what we call a DMA controller, a direct memory access controller, to take care of all the details. So all the processor needs to do is send the pertinent information to this DMA controller, and then the DMA controller does all the rest. Okay? And once the DMA controller is done transferring the data directly from the main memory to this external memory, it will then interrupt the processor and say, hey, we're done. What do you want me to do next? Okay? So in order to accomplish this, the DMA controller has to provide all the signaling on the bus. Remember, the bus has a number of lines. There are data lines, address lines, and control or command lines. Okay? And those control signals tell the various components what to do. So if the processor is no longer involved, it's the DMA that has to take care of all that signaling over the bus. The DMA is also going to have some storage buffers in it, basically registers, okay? Because, you know, the main memory and this external memory might not work at the same speed. So there's got to be a place to store stuff until, you know, depending on which way the data transfer is going, there has to be some place to store stuff while the slower device catches up with the faster device. Okay, so the DMA, it's exactly the same except we've added this DMA controller in between the system bus and these external devices. Okay? So in order to facilitate this, the processor is involved with the transfer of every word in a block of data, but it does have to send some information to the DMA controller in order to initiate this transfer. Okay? It's basically has to tell the controller the starting address. Let's say we're going to transfer a block of data from the computer's main memory to some external hard drive. The processor has to provide the DMA controller with the starting address of this block of data, obviously. And it also has to tell the DMA controller how many words of data starting at that address are supposed to be transferred. Okay, so in the DMA, there's going to be some registers, just like every external I/O device has some registers. One of those registers is going to hold the starting address of the data block. And so the processor is responsible for writing that address in here. And then the DMA controller knows it's going to start here. Okay, so this would be the starting address, for instance, in the main memory of the computer. The word count register will hold a number that corresponds to the number of words that need to be transferred. And the processor writes that as well. Okay, it also has to tell the DMA controller whether this is a read or a write operation. Okay, is the data going from the main memory of the computer to an external hard drive, which would be a write, or is it going the other way around? Okay, so this bit, there will be a bit somewhere in this control register which the processor will set to a 1 or 0 to tell the DMA controller the direction of the data transfer. Okay, there will also be an interrupt enable bit which will, if the processor sets this to a high, I think it says it down here, right? If interrupt enable is set high, the controller should interrupt the processor when the transfer is complete. Okay, so if the processor, again, would set this bit to a 1 or 0, depending on whether it wants the DMA controller to interrupt it when the transfer is complete. So those two bits would be set by the processor. The DMA controller itself would be responsible for setting another 2 bits in this word, one of them being the done bit, which means when the transfer is done, the DMA controller will put a 1 here, and now the processor can always read that bit to see if the transfer is 1, if the processor wants to do that. The DMA controller will also, if it's going to interrupt the processor when the transfer is done, it would set a 1 to this bit here. And that way, again, the processor could use this, could read this bit to find out, oh, it was this DMA controller that interrupted me, because its bit is set equal to a 1. Okay, so there's going to be some registers that control this. DMA initialization. Additional notes, processor and DMA bus requests are interwoven. So the processor is going to give this initial information to the DMA controller. The DMA controller is now going to transfer the data. That happens over the data bus. Okay, in the meantime, the processor is going to go on with whatever it's doing, okay, which may also need to use the data bus. Okay, so typically they're going to share the bus. The DMA controller will use it for a brief period of time to transfer some data, and then the processor will be able to use the bus to maybe go to main memory, get some data that it needs to do some calculation, bring it into the processor and do its calculation. So they'll share the bus by interchanging their use, right? They can't use it simultaneously, obviously, so one will use it for a brief period of time, another will use it, then somebody else will use it for a brief period of time. Typically, however, the DMA transfers are given higher priority. Referred to as cycle stealing. Yeah, okay. Alternatively, so that's when they're interwoven, right? Processor uses it for a bit, DMA uses it for a bit. Processor, DMA. Alternatively, what we call block or burst mode is where the DMA has exclusive access to the bus so it can transfer a whole bunch of data really quick, okay? In that case, well, the CPU basically is going to sit idle because it doesn't have access to the bus to do other things, but the transfer is quicker. So there's always pros and cons to everything, okay? Among DMA controllers, higher speed devices have a higher priority, and that's a general principle. The higher the speed of the device, the higher the priority. I mentioned this last day. You know, a dumb old slow keyboard doesn't need to be high priority because it's really slow already, right? Whether it takes a millisecond to get that character into the processor or whether it takes 2 milliseconds to get that key into the processor doesn't matter to you when you're typing, okay? So it's given a lower priority for going over the bus. If the processor and one or more DMA controllers tries to access the bus at the same time, these activities must be coordinated by what we call a bus arbitration procedure. So you've got a DMA controller now trying to access the bus, you've got the processor trying to access the bus. Sometimes they're going to want to do it at the same time, in which case we have to have some sort of mechanism to break the deadlock, okay? Who's going to be able to use the bus right now and who has to wait? We call that arbitration. Yeah, this is a little, they're related, you're right. But what we were looking at back here, block mode is based, we could have this where they alternate, okay? Which is not what we're showing in that other one. So there, yeah. Okay, so block mode or burst mode is basically what we were showing in the other one. This is one where there's more sophisticated circuitry controlling the bus. You got it for a while, you got it for a while, you got it for a while, you got it for a while. More sophisticated than what we just saw in this block diagram. Okay, so as we said, the bus contains data, address control lines, and timing information. We're going to talk about that in a few minutes, which is the clock signal. And the control includes lines needed for arbitration or interrupts. So the control bus will have lines over which a device will send interrupt signals, and there will have other lines in the control bus which deal with this arbitration. okay? And when we talk about arbitration, we're talking about how do we decide who's gonna use the bus. So typically the way it works is that you're gonna have one device, maybe the processor, but maybe it's the DMA controller, or maybe it's some other device attached to the bus, is gonna be the master. And whoever is the bus master has access to the bus, okay? They have the exclusive access to the bus for that period of time when they are the bus master. And if you're the bus master, well, then you're responsible for initiating any transfers over the bus. So usually it's going to be the processor, because the processor is the fastest thing connected to the bus. Typically it's the bus master, and it's the one controlling everything, and therefore it has access to the bus. But at times the DMA controller will be the bus master, and it will then have access to the bus, okay? The device being accessed by the bus master is what we call the slave or the target, okay? So if forget about a DMA controller for a second, if you've got a processor and a main memory unit connected to the bus, the processor would be the master, and it wants to get some data from the memory unit, while the memory unit would be the slave, okay? The processor would control the bus, it would initiate the transfer, send the control information, and then the slave would respond, which is the memory. So we've got a master and a slave. That was back here, right? Okay, in terms of arbitration, how do we determine then who is the bus master at any particular point in time? Because the bus master has full access to the bus. Once the bus master relinquishes its control of the bus arbitration, some sort of circuitry, is going to be used to determine, okay, who's the next bus master? And that's typically the next device that has made a request to use the bus. Okay, so this arbitration procedure requires devices to make a request of the bus arbiter, which is just a circuit, a bus arbitration circuit, to say, hey, I need to use the bus, may I have the bus? And then it's the bus arbitration circuit's job to decide who gets the bus at this point in time. Yeah.
Does that slow things down?
It does, but there's really no way around it, right? You can't, otherwise you'll have collisions on the bus if two devices send at the same time. Yeah, but yeah, it takes time to do this, right? Lock mode, sophisticated. Okay, so we could have something like this. So here's our bus. We've got some input-output devices. You know, one of these might be a DMA controller, or just an external hard drive without a DMA controller. We've got some other devices here. One of these might be a processor, for instance, okay? What we'll have is some arbiter circuit, which is going to accept, BR stands for bus request, BG stands for bus grant, okay? So these different devices that are attached to the bus, if they need to use the bus in order to transfer some information to a different device, say master 1 requires use of the bus, it's going to send a signal on the bus request line to this arbiter circuit. If nobody else, if there's no pending request for the bus, the arbiter circuit will say, oh, you need the bus? Yep, nobody's using it. This microsecond, you can have it. And it sends a signal, a bus grant signal, back to the master, and now the master knows, okay, I can use the bus. And it does its transfer, okay? When some other circuit needs, or other device needs the bus, it does the same thing. It sends a bus request signal. If the bus is currently free, the arbiter circuit is going to send a bus grant signal back. If it's not currently free, well, then the arbiter circuit doesn't send this signal, and this device has to wait until it gets the okay from the arbiter circuit. Okay? So that's the general concept. It's not rocket. This is not a computer. This is not a processor. It's basically some logic gates, right? Because what's going on, more suppression, signs or anything like that. So some devices may have a priority over other devices. Again, usually faster devices are given priority. So let's say we've got 3 different devices, each with their own bus request and bus grant lines connected to this arbiter circuit. And let's say that the priority has been set that device 1 has highest priority and device 3 has lowest priority. Okay? So the timing will work something like this. So obviously time is in this direction. Okay, time is in that direction. So let's say that the first device to actually assert its bus request signal is device number 2. Well, at that point in time, bus request 1 is low and bus request 3 is low. So device 2 is the only one who's saying, I need the bus. Okay, so it sends that signal. The arbiter circuit receives that signal. And since nobody else is currently using the bus or asking to use the bus grant signal goes high, meaning the arbiter circuit's telling device number 2, you got it. You're the bus master. Okay? This bus request is going to stay high for as long as that device needs the bus. Okay, so it takes some time to do the data transfer, at which point when that's done, that device is going to drop its bus request signal, telling the arbiter circuit, I'm done with the bus. Okay, that tells the arbiter circuit, okay, I'm done with the bus, at which point in time the bus grant signal is dropped by the arbiter circuit. So now device 2 is no longer the bus master. Okay. Well, while that data transfer was going on, while device 2 was the bus master, device 3 also asserted its bus request signal saying, hey, I need the bus. Since since device 2 has higher priority than device 3, that doesn't change anything, right? Currently, device 2 is the bus master, so this is ignored by the arbiter circuit, okay? So device 3 waits and waits and waits and waits until it will eventually get its bus grant signal from the arbiter circuit, okay? So it's waiting. At this point in time, right here, device 1 decides it needs the bus. So it asserts its bus request signal, okay? Well, device 2 is still using the bus. So device 1 also has to wait, okay? We don't interrupt. Eventually, device 2 is finished, it drops its signal. The arbiter circuit says, okay, I'm relinquishing control of, you're relinquishing control of the bus, you are no longer the bus master, device number 2. At which point in time, at this point in time, it looks and says, well, who else is asking for the bus? Well, 1 and 3 are both asking for the bus. 1 has priority, so therefore, the arbiter circuit is going to assert its bus grant signal to device 1. And now device 1 is the bus master, okay? It starts doing its data transfer. Device 3 still has to wait because it's lower priority. When device 1 is finished, it drops its bus request signal. The arbiter circuit now knows device 1 is done, so it drops the bus grant signal. Device 1 is no longer the bus master. It then looks and says, well, does somebody else need the bus right now? Oh yes, device 3 is still waiting. Now it becomes the bus master and finishes its data transfer, and then it relinquishes control of the bus. Okay, so that's basically what happens, yeah.
How does the arbiter know if the bus is being used?
By the bus request signal.
And so the ground will like not give it to any other, I guess, master unless the request signal is down.
Right.
Okay.
Yeah, as long as a device keeps its bus request signal high, it's using the bus. And the arbiter circuit won't interrupt it. Yeah. Is there another one over here? Oh, sorry, yeah.
How sophisticated are these circuits? Because it kind of seems like this could be done with just a few latches.
Yeah, it's not very sophisticated. This bus arbiter circuit, in its simplest sense, all you gotta look at is these bus request signals in order to figure out what these bus grant signals are. It's basically combinational logic or something, maybe a little more sophisticated because we're just showing the high level view of it, right? But yeah, they're not sophisticated circuits. Yeah.
Would you be able to elaborate on the distinction between block mode and bus arbitration?
Between what?
Block mode and
Here, right? We send, while this one is sending a block of information, we don't interrupt it. In more advanced, any other questions? Yeah.
Yeah, I'm not entirely sure what parallel computing.
Sorry, what?
Parallel computing would entail, but
So parallel computing, you're talking about multiple processors?
Yeah,
That's a good question.
because it seems like it'd be a little bit wasted if you were just using one bus.
Well, yeah, but I'm not sure how you could, like, there's only one address port, if you want to call that, on a memory unit, right? So even if you connected it to two different buses,
Yeah,
you can only use that port one bus at a time.
right.
So I'm not sure that multiple buses would even work in that case. But that's a quick, I don't know the answer to that. Sorry. Okay, so that's bus arbitration. All right, so let's start looking at buses. There's two basic types of buses. There's what we call synchronous buses and asynchronous buses. Synchronous buses work using a clock, okay? And the clock is just a square wave generator in the processor, which generates a clock, a square wave at a certain frequency, right? And when you read, when you read the specs for a computer and you say, well, this operates at, I don't know how many gigahertz these days, they're talking about the clock speed. How fast is this clock? And so in a synchronous bus, everything happens on edges of the clock, okay? Nothing happens in the middle. It happens on the edges. So obviously, the faster the clock, the faster things are happening, right? Asynchronous buses don't happen on the edge. Things don't happen on the edge of the block, on the edge of a clock. We use other control information to determine when things happen and how other devices recognize that some other device has done something. But with a synchronous, and we'll talk about those next, but in a synchronous bus, everything happens on the edges of clocks, of the clock signal. Consequently, this clock signal is one of the control signals that is sent out on the bus by the processor so that every device connected to the processor has access to the clock. Has to happen, right? And so everything is synchronized amongst all the different devices, right? Like when in the movies, they all set their watch to the same time, they're synchronizing so that, okay, at this particular time, we all know something's happening. And at this particular time, we all know something's happening. So if we talk about, and the examples we're going to use here, obviously there's a lot of different things that happen in a computer, but one of the most common things that happens over a bus is transfer of information, right? Where we go and we read a word from memory and bring it into the processor, or we write something from a processor register to memory, right? So it's going over the data bus. So that's what we'll use, read and write operations, or input and output operations over the bus, we'll use as our example as we discuss these buses. So in its simplest form, for instance, reading a data word from memory into the processor could be done in one clock cycle, okay? So let's see what has to happen. Well, the first thing that has to happen is that the master, which is the processor, for instance, the bus master, has to place the address on the address lines of the bus that it wants to read a word from in memory, okay? So we've got the bus clock signal, we've got address and command signals. We don't show every single address and command signals, it's just one set of signals. And you'll notice that we've got two lines here, which indicates that there's a number of different lines on the control bus and the address bus, and some are high and some are low depending on the number in the address, for instance. Okay, so that's why it shows two levels here. There's a bunch of parallel lines here. Some are high, some are low. Okay, that's what's shown here. These transitions show that at this particular time, the information on the address and control bus is changing, okay? So at this particular, on the rising edge of the bus clock, the processor is going to put a new address on the address bus and some new control information on the control bus in order to read this word from memory, okay? So that's what's happening here at time t0. Okay, well, that information travels across the bus to all the devices out there, okay? And one particular device, the main memory unit, will recognize the address on the address bus. It'll go, oh, that's one of my addresses, okay? Everybody else will go, nope, don't recognize that address, I get to continue sleeping, I don't have to do anything right now. But the one device that does recognize it, well, it knows it's got to do something now. So after this has been placed on the address and command lines, the device has to decode that data, okay, which takes a little bit of time. We're going to keep talking about that. On the next edge of the clock, which is a downward edge, the device is going to do something. So on this clock edge, the master did something. It put the address and control information on the bus. On this edge, the device does something. What does it do? It puts the data that's at that address in its memory unit onto the data bus. Okay, so that's what happens here at T1. Okay, so that's represented by this here. Again, there's a number of different lines on the data bus. Some of them are high or low, depending on the word that's being transferred. Okay, so, and it changes here. So now we've got, for this time here, we've got data on the data bus from that address in the memory unit. On the next edge of the clock, the master, the processor, is going to read that into its flip-flops, its latches, okay, into a register. So that's what happens here, and at that time it says, okay, I've got that word, I can now go and get the next word from memory, for example. So it changes the address and command information on that part of the bus. Okay, and at the same time, the memory unit is going to drop the data off of the data bus. Okay, so everything happens on clock edges. So you might ask, okay, well, if everything happens on clock edges, why not make this smaller or make the clock frequency higher, right? Well, yes, that's what we try to do, but there's limitations because not everything in circuitry happens instantaneously, right? It takes time for these signals to propagate down the wires or the traces on the printed circuit board. It's really fast, obviously. It's almost the speed of light, but it still takes time, okay? There's also other delays that we're going to talk about in the next couple of charts, but that's the first one, okay? So that's the basic idea of a synchronous bus. Everything happens on clock edges. The processor asks for the word at that memory address by putting the information on the control and address lines. The memory unit puts the data on the data bus. At the next edge, the master reads in that data and changes its address and command information to perhaps do the next word. Okay? So there are some reasons, though, why we can't make this bus signal at a higher frequency. Like I said, master to slave propagation delay. There's some fixed amount of time that it takes for these signals to travel down the bus to all the devices, and then it takes some time for those devices to decode that. They have to look at this address, and they have some circuitry which determines, yeah, that's one of mine, or no, that isn't one of mine. That takes time as well. Okay, so we can't just make this really short. We have to account for that time. On the second half of the cycle, again, now at this point in time, the slave, the memory unit, puts some data on the data bus. That takes some time for that data to travel down the data bus back to the processor. Okay, so there's some propagation delay too. Once it hits the processor needs some amount of time to set up its flip-flops in its register that it's going to read this data word into. And if you don't know what setup time is, you can look at the gory details in Appendix 1, I think, or Appendix A of the textbook. Okay, it's just, you can't, it takes a finite amount of time to load values into a register. It doesn't happen instantaneously, okay? So we call that setup time. So those are the delays. In actuality, it looks like this, and we'll talk about this on Friday. Have a good couple of days, and we'll see you then.